Hi friends, this is Shomik Bishash. Today I am giving you one lecture on maximum power transfer theorem. We are attending the class of network theorems applicable both on AC and DC network. So our today's topic is maximum power transfer theorem. So what is the condition of this? Now if I am writing the condition of that maximum power, here I should write maximum power transfer theorem. So today our topic is on DC. So in a DC circuit, if you are using this rule, so the condition is this. So what is the condition? That in the maximum power transfer, that is V by R plus RL whole square, and that V square, so this is the P actually, so P into RL. Okay, so actually I'm sorry, this is V by R plus RL, this is not P, this is I square into RL, so that is equals to the power P. Now one condition is coming, that what is the R and RL relation to be the maximum power on the load. Here it is RL, so the condition is R equals to RL. Now how that R equals to RL is made, it can be easily done by taking the differentiation of this. So it can be easily proving that how it is coming in this particular form, R equals to RL. Now the maximum power transfer theorem, we have applied that particular maximum power transfer theorem in that DC circuit and that AC circuit. So in the first problem I am applying these things on the DC circuit. Here it is given as 5 ampere, it is 2 ohm resistance, that is R, that is 5 ohm resistance, that is 10, and that is 24. So we have to find out the value of maximum power can be delivered to that particular R. So how to find out this maximum power? Actually we have to use either Thevenin's or Norton's theorem to get that value of I or V. Okay, if you are getting V, so V is the output, sorry, the open circuit voltage, so it is V Thevenin you can write. So V Thevenin, that is V square if you are taking by R, it is the answer, R plus RL. So that is a current, so obviously across R you can find out, or you can have that I using this Norton theorem. So let me apply the Norton theorem and let us discuss what are the drawbacks, what are the problems the people used to face with this. So if you are using Norton's theorem, so what is step number 1? In the step number 1, first of all you have to use this is as 5A, this is 2, this is, just make it first of all open, and that is 5, that is 10, that is 2.4 amps. Now why I did this, not necessary, but I'm just making the same particular voltage source as the current source. Okay, so here the shorted is made. Okay, so the voltage here is VA and VB, right? So what is the voltage gap between VA and VB? How to find it out? So initially, what is VA? So now it is 5, this is 2, so the drop is here 10 volt. So VA equals to 5 into 2 equals to 10 volt. Now what is VB? VB equals to 2.4, having this type of parallel resistance. So what is the voltage drop across this? You have to find out. So if you are doing this, so it can be easily shorted out as the current is dividing in 1:2. So here it is 2/3 is flowing in this and 1/3 is flowing in this. So finally, what is the voltage drop across this and across this? They are in parallel combination. So I can again make it as 5 for the simplicity of design and 24. So it is 10, this is 5. So what is the voltage drop across this? This is 24 by 15 into 5. So this is 8 volt. So 8 volt. So what is that voltage gap? This gap, the voltage gap is VOC. This is 10 minus 8 equals to 2 volt. Okay, now what you have to find out more, that is what is the value of R. Now if you are looking from this particular direction, if you are looking from this, so obviously 5 and 10 and 2, so there will be 5 parallel 10. That combination is series with 2. So this is 50 by 15 plus 2, so it is 3.33 plus 2, so it is 5.33. Okay, so if it is 5.33, so we will be having this particular V, we are having this particular one. So what is the maximum power here? That power is VOC square by 4 RL. That is the maximum power. Why? Because if you are putting R equals to RL in this equation, it is maximum in that. If R equals to RL, so it should be V square by 4 RL or R, whatever. Now that is VOC square by 4 RL. So just put this value, that is 2 square by 5.33 into 4, so it is approximately 188 milliwatt. Okay, that is using Norton's theorem. Okay, now to finding out that Norton current in this particular branch, so we may have different sort of idea that you may have in that another approach, say approach number 2 here, that is 5A and this is 2, this is shorted, this is again 5, this is 10, this is 2.4. Actually I have invented that particular way for this type of problem of solution, so I need to use this again in the other way. Just play with this. A is shorted. Okay, so finally if it is shorted, so what is the current flow? For this is active, this is off. So if it is off, so it is open circuited. So finally the current flow is taking this branch and these two branches. So what is the summation of these two branches current flow? It is basically the current for 5 ampere, right, this direction. So what is this? How to find out? So here the total current is taking the division half is to 1 by 5 is to 1 by 10. There is a resistance ratio 2, 5, 10. So current taking the reverse ratio, that is I1 is to I2 is to I3. So if you are finding out the all total here, so finally this is I1 plus I2 plus I3 equals to 5. So if you are taking the ratio, so it is 1 by 2 plus 1 by 5 plus 1 by 10 into K, that is equals to 5. So 4 by 5 K equals to 5, or K equals to 25 by 4. So if it is 25 by 4, so what is the current flow in this particular branch? Into half, that is equals to 25 by 8 ampere, okay, for this branch. So what is the rest portion? That is 5 ampere minus 25 by 8. So it is 40 minus 25, so it is 15 by 8 ampere, and this way. And what is this? Is 15 by 8. So, and if you are taking this particular one, so what is the current flow? You have to calculate it out. So finally for this, if it is shorted, so the current is taking this path and this path and this path. So finally this is the same way, that 2.4 equals to 4 by 5 into K. So here it is 120, that is 4. So it is basically 3 equals to K. So what is the current flow in this particular branch? So these two branch having that current flow, so obviously current flow in this branch is I by 2. So it is 3 by 2 ampere equals to 1.5. So that is 1.5, and that is 15 by 8 ampere. So 1.5, so what is the value? You can see that is 1, that is 1, and this is 0, 8, 1.08. okay. So as you can see here, that is 15 by 8 I have evaluated right here. So it is 25 by 8. Actually the current flow here, I did a little bit mistake here, so it not be there. So actually that is 25 by 8. So here this current actually 25 by 8. So if it is 25 by 8, so it should be 3.01. So approximately it is 3, and that current flow here it is 1.5. So using that superposition theorem, the final current ISC equals to 3 minus 1.5 equals to 1.5. Now it is 1.5. now it is 5.33, this particular one. Okay, so if you are multiplying this 1.5 into 5.33, that is equals to 7.995 approximately 8 volt. So it is considering from this region actually. So the net current is this 1.5. okay. So what is the Thevenin, what is the Norton equivalent circuit? Here you can write it as the current source I 1.5 ampere. Here that R is unknown, here it is RL, what is 5.33. so it is a Norton equivalent circuit. Now actually in my note I gave it in some other way. So here you have to use that Thevenin's theorem. So I am just making X and Y, these 2 points is open, and that 5 ampere and 2 ohm resistance, that is in parallel combination, we change it 10 volt and 2 is series. So it is XY, this is 5, this is 10, this is 24. So what is the open circuit voltage here? That is 24, 5 plus 10, I did it here, that you can see. Yes, so here I hope you can see it right now. So how I did it is, say this is I, you have to find it out, that is 1.6. so what is the drop across 5? This is 8 volt. Okay, so this is 8 volt drop right here, and here that is using KVL, 10 volt minus 2I 8 volt equals to 0. So obviously we know that VOC has to be 2 volt in this equation, right? Because I equals to, already calculated out, so that open circuit voltage equals to 2 volt. So what is this actually? 10 volt, this is open circuit, so that drop is here 10 volt, and that is 8 volt, so 8 minus 2, that is 2 volt in this region. So I have just applied this one, RTH, I have calculated out, plus 2 is 5.33, and P max VOC by this, so it is same answer, 1.88 milliwatt. So again I am saying that whatever the method you are following, whether it is nodal analysis or mesh analysis or KVL or KCL or Thevenin's and Norton's, anything else, so the answer must be the same. Here again I have proved it by my method, and there in this copy what I have shown, this particular method, both are having the same answer. Okay, so here one problem from the AC region, that maximum power transfer you have to find it out. Here one impedance 6 minus J8 is given, another is J8, and this is ZL. So you have to find out the maximum power through this. So first of all you have to remove ZL, so find Z Thevenin, that is equals to that parallel combination of these two resistance. You have to find it out as ZTH equals to this, and finally this particular value 10.67 plus J8, that is coming. So again it is VTH, it means the VOC. VOC means what? Actually the open circuit voltage here. So if you are moving it, this one, so you have to find the open circuit voltage, that is the current drop in this particular one. So the entire circuit is this. So after passing to this resistance, what is the drop? The drop is this one plus this one into this particular point voltage drop. So it is J8 by 6 minus J8 plus J8. So 10 plus angle 0, it is given, as you can see this. So finally it is 13.33 into 90 angle, this volt. Okay, so finally the maximum power, so obviously ZL equals to ZTH. Okay, here it is a complex conjugate, so I make it as a star. So what is the value of ZL? That is 10.67 minus J8. It is plus, so it is minus. So what is P max? That is V square OC by RL. That open circuit voltage we have calculated, that is 13.33 angle at 90 degree. So just putting this value over here, 4 into RL the power is always the real factor, so we should ignore that imaginary part. Okay, so just putting this real value, and finally it will be getting as 4.163 watt. Okay, so that is the two example I did for the maximum power transfer theorem, one for the DC analysis, another is for the AC analysis, and I have shown that these all are the methods simply. So this particular theorem here I have used the Thevenin's one. In the back in that copy I have used, this is the Norton's application in the both way. And this is a direct Norton application. This particular one is called the superposition theorem. I have used once for 5A, another for 2.4. So the answer will be same as we are getting, that is ISC. So here if you are having this 5.33, so now that total, if you are dividing this particular one, you will be obviously getting that VOC. If you are getting VOC by R, it will be the ISC actually. So they are quite similar to each other. So two methods here and here I have used. Now in this case I have used the Thevenin's theorem application, the same problem, and getting the same answer, and that is the maximum power transfer theorem for the AC circuit. I have worked it out entirely. So for your suggestion for you all, so please do practice a lot of more on this particular one, and shuffling of theorems from one to another to this, it should be carried on by you. In future much more complicated problem, much more university standard, more problems which is coming to the different type of question, different type of examination like GATE and others, I will discuss in this same forum. So read all those things carefully and try to practice by yourself. Wish you all the good luck in future. Thank you very much. And my early class and the last class of this section is that Milman theorem. Okay, so in my next class I will discuss this Milman theorem and both its problem in AC and DC. So thank you very much. See you all the next. Goodbye.